Welcome. In this video, we'll be looking at rational Z transforms. So let us revise what is Z transform. Xz is simply x of n z to the power minus n summed over all n. And let us look at one very common example. Let's say x of n is delta n minus 1, simply a delay. How will the x of z look like for this? So x of z is simply sum over all n, xn into z minus n. So this will be 1 only at n equal to 1. So let us substitute n equal to 1 here. So we get z power minus 1. Now you know why we represent a time delay block with z inverse. If there is a delay by one step, then we call that block z minus 1, if you remember, like this. Right? Okay. This was just a recap or just a clarification for some concept we discussed earlier. Now let's come back to rational Z transforms. So Z transforms for LTI systems, and one very pertinent class is rational transforms. Let's say xz is a rational function of z, means it is some numerator which is a function which is a polynomial in z, and the denominator is also a polynomial in z. So both are polynomials in z. Okay, and you can compare it with the LCZE, a linear constant coefficient difference equation representation for LTI systems, and you will see some very nice correspondence between this kind of rational Z transforms and the LCCDE systems which can be represented with LCCDE representation. Okay. Now this brings us to a discussion on poles and zeros. Okay. Now our numerator p of z and the denominator d of z can be factored. Remember, these are polynomials, so I can factor them to find roots of these polynomials, right? So let's look at this form of z. So p of z can be written in this form, that it's the product of z minus the roots of the polynomial. Let us call them as zeta L. L goes from 1 to some capital M, and the denominator is z minus lambda L, and lambda L's these are the roots of the denominator polynomial. And in this way, so if you see, this term and this term are very important. Now, what are zeros? The zeros of xz are the roots of the numerator. Why they are called zeros? Because at these zeta L's, the value of x is 0, right? So this is why it is called a zero of x of z. And now again, poles of x of z. What is a pole? Pole means high up in the air, so which means x of z approaches infinity. Of course, it cannot be infinity absolutely, but this is the value approaches infinity as the z approaches lambda L. So these are the roots of the denominator. That is why these are called the poles. Let's take an example to get a more clear understanding of this concept. Let us take a rational gz, so which is simply this form. Now find its poles and zeros. Very easy. Roots of any quadratic equation. You see both the numerator and denominator are quadratic equations, and you know the roots are given by this formula. For numerator, I can find the roots, and which comes out to be, the two roots are 1 and minus 2. And for the denominator, the roots can similarly be computed, They come out to be 3 by 2 and 2 by 3. What can we do with these? So our GZ can be written like this. The zeros are the roots of the numerator, 1 and minus 2. Poles are the root of denominator, 3 by 2 and 2 by 3. And I can represent GZ in this form, right? So simply in the factored form. Now, let's discuss another concept called a pole zero plot. What is a pole zero plot? In any z space where the real part of z and imaginary part of z form the two axes of this plot, I know my z will be, my x of z will be exactly 0. This will be, x of z will be exactly 0 when my z is 1 and minus 2. So when z is 1, the imaginary part is 0, real part is 1, then value of x of z is exactly 0. I represent that with a circle. And similarly at minus 2, it's a circle. These are the zeros. So this one and this one. These are the zeros of x of z. And the roots of the denominator, so basically 2 by 3 and 3 by 2. These are the poles of x of z. Right? So we represent the poles with a cross and zeros with a circle. Now you know that x of z can be computed for any value of z, right? It's just a function of z. And how will it look like? If I plot the mod of x of z, so the absolute value of x of z with respect to z, basically z is a two-dimensional surface now. This is how it looks like. You can see at 2 by 3 almost, this is shooting very high value to high value, and at 3 by 2, it shoots to a very high value. I know this plot is not very clear, and you know, if you want to see a clearer form, then you should not be plotting mod of x of z. Rather, you should be plotting log of mod of x of z. So this is how it will look like. The 20 log to the base 10 mod of x of z. So why 20 log? Because I have used so that this can be represented with the decimal units, right? And then the plot looks much cleaner. You see exactly these are the zeros. And these are the poles where the value of x of z shoots very high. And if you look at the y-axis or the imaginary axis, it will be exactly 0 at these points, and the real axis will be the values which we obtained, plus 1 and minus 2 for the zeros. You can see minus 2 here and plus 1 here. So in this way, you can plot the surface of x of z. The references for this section are Oppenheim, chapter 3, the Z transform, and there is a nice book called Sanjeet Mitra, Digital Signal Processing, which I found a very good book. You can look into this book as well if you wish. Chapter 6, Z transform. Thank you very much.